All right, welcome. Let's work some related rate problems. This is going to be just more slightly more advanced related rate questions. You know, the cone, the shadow, what else? Other triangle situations. I don't know. We'll figure it out. So, okay. Let's start with a cone is 4 meters across. I'm going to sheet of paper to work on. Cone is 4 meters across and 4 centimeters across and 6 centimeters deep. Okay, so I'm going to draw the picture. I've got a cone like that. Water leaks out from the bottom at a rate of 2 cubic centimeters per second, so dV dt equals -2. How fast is the water level dropping? What is dH dt? And when the height of the water is 3. So 4 centimeters across, meaning the radius is 2 and the height is 6. Okay, I know this is a cone situation. I always need to leverage that similarity relationship. So I'm going to say R over H equals 2 over 6. If I'm looking for dH dt, and I have H, I need to get rid of R in the volume formula for a cone, which is 1/3 pi radius squared multiplied by height. So I need to get rid of radius, right? So I can work just in H. So I'm going to say that that means that R is multiplied both sides by H. R is 2/6 of H, or 1/3 of H. Okay, so that means 1/3 pi. Radius is 1/3 of H. I square that, I get 1/9 H squared, and then I'm multiplying by that H. So this is pi over 27 H to the 3. Okay, this is V. Now I'm going to take the derivative with respect to time, and that's 3 pi over 27 H to the 2 dH dt. And if the height is 3 and dV dt is -2, so 3 times 3 squared is going to be, that's just going to be pi dH dt, and that means dH dt equals -2 divided by pi. Okay, number 2. A person that is 2 meters tall, that's a pretty tall person, walks toward a street light on level ground at a rate of 0.5 meters per second. Okay, with this one, you got to draw the diagram. Okay, this is the street light, sun on a stick, and then there is a person, okay, which is going to be in line with the light, and then, okay. I have in the past typically called this length here W and this one X, W for shadow, X for just horizontal distance. And okay, but the person is 2 meters tall. The light on the post is 5 meters tall. So well, basically, the person is 3 meters from the post, X equals 3, dx dt is -0.5. Okay, and X equals 3. So what happens is that you use the similarity relationship. 5 over this whole length is the same as 2 over W. So 5 divided by X plus W equals 2 divided by W. And hopefully once I cross multiply and get all this set, I'll have everything that I need to substitute and then take the derivative and get myself an answer. Length of the person's shadow is decreasing. Yeah, that would be true. All right, so what am I doing here? So I'm going to cross multiply. 5W equals 2X plus 2W. Subtract 2W, I get 3W equals 2X. This is the type of relationship I can take the derivative of implicitly. So 3 dW dt equals 2 dx dt. So not really sure why we needed the value of X. But I'm just, if it's that critical of an error, I guess I'll just have to re-record the video. But I don't see what that actually has, how that's impacting the situation, because it's a proportional relationship, which is linear, so I think it's not relevant. So what I'm saying is I think the rate of change of the shadow is going to be constant if the rate of change of X is also constant. So anyway, dw dt is what I'm hoping to find, equals 2/3 of dx dt is -1/2, and so that's going to be -1/3 of a meter per second. Number 3, a boat is being pulled into a dock by an attached rope, where is it, that passes through a pulley on the dock, positioned 6 meters higher than the boat. Okay, so this is going to be the front of the boat, and the pulley is up here, meaning this is a distance of 6, whoops, pardon me, and 8 meters from the dock is going to be 8. Okay, yeah, if the rope is being pulled in, so I guess this is R, the RDT is -3 because there's 3 less units of rope. How fast is the boat approaching the dock? So really x equals 8 and y equals 6. And these things are changing with respect to time, right? As we pull in the... but this is fixed. Okay, so this one won't be so bad. Right, we know that x squared plus y squared equals r squared, meaning that 2x dx dt plus 2y dy dt equals 2r dr dt. Okay. Now what I'm thinking is that, what am I thinking? Oh, dy dt is 0 because the height of the pulley is not going to be changing, right? I'm just going to wheel in that rope from right there. So the boat is getting closer to the dock, leading me to believe that, okay, dy dt is 0. So 2 times x times dx dt, which is what I'm hoping to find, equals 2r dr dt. Now, when x is 8 and y is 6, that's twice as much as the 3, 4, 5 triangle, right? 3, 4, 6, 8. That means r needs to be 2 times 5, and that's going to be 10. And dr dt is, what is it, -3. All right, so we're going to scoot that up a little bit, and I'm going to solve for dx dt, divide by 2, and I'll get -30 divided by 8. Probably meters per second. All right, number 4. The height of a cone is 12 and the radius of the top is 3. Okay, this is going to be very... Okay. I kind of wish I'd asked this one differently because this is the exact same problem as before, but that's what you need. That's what you're going to be hit with on the test, is one very similar to this. So radius of the top is 3, height is 12, volume is 1/3 pi radius squared h. And this cone formula, this cone volume formula, is always given to you in the state of the question. I just didn't do it this time, I guess, because I thought you could go look it up, or I would put it on this video. All right, so again, radius, I'm going to just kind of jump to it. Radius is 1/4 of height, regardless of where you are, you know, if it's filled up to here, or if it's all the way full. Radius is going to be 1/4 of height because of the similar triangles. So volume is going to be 1/3 times pi times radius squared is going to be 1/16 of h squared, right? Because I square both of these, and then I multiply by h. So v equals pi over 48 h to the 3. Okay, very similar to an example I think I worked in class for you. So what am I going to do? Oh, I'm going to take the derivative with respect to time. How many problems are on this set? 7. Okay, that's fine. dv dt is 3 divided by 48 h to the 2 times the derivative of h with respect to time for the chain rule. So I'm going to plug in when the depth of the water is 7. Okay, so when h is 7, dv dt, they said, poured in at 4, so 4 equals 3 pi over 48 times 49 times dh dt. Right, so, I mean, there's all sorts of things you can do, but I'm just going to solve directly for dh dt by multiplying both sides by 48 and dividing by 3 pi and 49. And that will be a suitable expression for dh dt. Right. Right, a 6-foot tall person. This is another shadow and walking question. So hold on, let's say flat ground. So that's the shadow, that's X. The height of the lamp is 15 feet, and the height of the person is 6 feet. And okay, walks away at 2 feet per second. So dx dt is positive 2. So we know, again, 15 divided by this whole length is equal to 6 divided by w. And we're going to cross multiply. I'm going to solve to get just all the variables on, each variable on one side. Okay, so 9w equals 6x. Take the derivative with respect to time. Right, and then I'm going to say, well, what am I going to say? 9 dw dt, that's what I'm hoping to find. Dx dt is 2, so dw dt is 6 times 2 is 12 divided by 9. Okay, and then that's, probably in feet per second. All right, so the next one is a conveyor is dropping sand onto a cone-shaped pile at a rate of 100 cubic feet per minute in such a way that the height of the pile is the radius of the pile. Okay, I'm going to have to draw a picture of this. So we got ourselves a cone-shaped pile that we're just, like dropping sand on from above. And somehow the height is always half the radius. That's radius, and that's 2 radius. How quickly is the height of the pile changing when the height is 10 feet? Well, if I want dHdt, I probably shouldn't be writing this in terms of r then, right? I'm going to probably say that if the radius... Wait, the height is half the radius. I don't think I even wrote that right the first time. The radius is twice the height. So I've got height and twice the height. Yes, because it's a wide pile. And so now I'm going to say, I'm going to just do it like this. So volume is equal to 1/3 pi radius squared multiplied by height. So now I'm going to substitute on radius, and that's 2 heights. 1/3 pi radius squared is 2h squared multiplied by h. So that's going to be a 4, so 4 pi over 3, 2 powers of h, another power is 3 total powers of h. So I've got myself a formula for volume in terms of h. So I take the derivative with respect to time, and the rate of change of volume with respect to time is going to be multiplied by 3, and I get 4 pi h squared, that's nice, times dH dt. Oh, that's very similar to the cone situation, which probably best we don't think too hard about that. Conveyor dropping onto the pile at a rate of 100 cubic feet per minute, so the volume is increasing 100 per minute. So 4 pi, h squared is also 100, and dH dt is what I'm hoping to find. So I could probably just, solve for dH dt, divide both sides by 100, and I'll have 1 over 4 pi. All right, and the last one is, yes, an angle of elevation type problem, which that's probably good for us. So an airplane is flying toward a radar station at a height of 3 kilometers above the ground. Let's say that's the height of the airplane. The diagonal distance between the airplane and the radar station. Okay, I guess we have to assume the radar station is sitting on the ground. So X is going to mark the spot of the radar station. The diagonal distance, I have to think that I meant this. I don't remember this problem. I don't know if I've ever worked this problem before. The diagonal distance between the airplane and the radar station, maybe I'll call that R. And, all right, horizontal distance is 5 kilometers. I'm going to call that X. Right. Okay, so we want theta. The rate of change of theta is what I'm hoping to find. And, you know, as much as I would like to use... I think what I'm going to do... this is unchanging. So it has a zero derivative. Meaning, I just want to use that in my... So I'm going to use sine of theta. And, oh, I guess you need that for the derivative of sine being cosine. Okay, I see where we're going. So, sine theta equals 3 divided by r. 3r to the negative 1. Take the derivative with respect to time. Cosine theta d theta dt equals negative 3r to the negative 2 dr dt. And so I think from here it's just going to be plug in the stuff and solve for d theta dt, right? Oh, okay. So I'm going to have to find out what r is, right, to find out what cosine is. But I can do that. And I'm going to, let's just plug the stuff in. So if this is 5 and that's 3, r equals the square root of 9 plus 25 is 34. Okay, that's probably not ideal, but we can work with it. Cosine theta is going to be the adjacent over the hypotenuse is 5 over root 34 times d theta dt is what I'm hoping to find. Negative 3 over r squared is 34. Well, at least there's that. Times dr dt was what? Negative 400. Okay, so I think I'll solve for d theta dt and start by multiplying both sides by the square root of 34. So positive 1200 square root of 34 divided by 5 and 34. And that's going to be... Does that make sense? Yeah, okay, as the airplane is... let's see, I used to be able to draw an airplane. That's not going to be a very good one. It's got the landing gear down. Got a, I don't know, a wing out or something. And I'll get a cockpit, a couple of windows. Maybe that's worse. What I'm saying is if the airplane's flying that way and we're staying a constant distance above the ground, the angle of elevation is going to be increasing because you're just going to have, if you're looking here and you're looking out, you're going to have to look higher up the closer the airplane gets. I mean, we know that. We've watched an airplane fly overhead before. Okay, that's all I've got for this video, I think.